In this video, we're going to find relative extrema of this function z equals x squared plus 3y squared times e to the negative x squared minus y squared. In the last video, we found the critical values. So if you need to find the critical values, if you want to watch a video of me finding the critical values, please watch the last video. That's where we did all of this work. Just as a recap, the way we find critical values is we find the gradient vector, we set it equal to 0, and then we solve for x, y. And of course, we're also looking for any x, y in the domain of the function for which the gradient is undefined. So we compute the partial of f with respect to x. It required the product rule. We factored it. We found the partial of f with respect to y. It required the product rule. We did that, and then we factored it. And then we set both partials equal to 0 at the same time. And remember, we were looking for xy pairs that satisfy both of these. So this represents a curve, and this represents a curve. These are curves in the xy plane. They're obviously not functions, they're relations. So we're going to draw these two curves, and then we're going to see where they intersect. And it turned out that these two curves intersect at 5 points. In order to find the points of intersection, the xy that satisfy both of these equations at the same time, we take each of the factors of each of the partials and we set them equal to 0. We have to be very systematic about it. We have to think about all the possible ways that this partial would be 0 and this could be 0 at the same time. So we just ended up with a couple of cases. The partial of f with respect to x is 0 if 2x equals 0, which means x equals 0. And then if x is 0, that meant that y would have to be plus or minus 1, or y would have to be 0. So that gave us those first 3 critical values. And then we also said, hey, this could also be 0 if this is 0. So we're on this ellipse, x squared plus 3y squared equals 1. We said if that's true, and the partial of f with respect to y is 0, then it turned out that y would have to be 0, and then if y is 0 and we substitute that in over here, we get x is plus or minus 1. So we got 2 more critical points from this. So that's the recap. If you want to watch me work it out, you can look at all those details in the last video. We also talked about why we're doing this and what all these things mean in the last video as well. So okay, we found the critical points. Now we want to know, does this critical point correspond to a min, a max, saddle point, or is it impossible to tell? And the same thing for all the rest of the points on this list. So also in the last video, we introduced the second partials test. And that's what we're going to use here. We said, find the Hessian. That is our multidimensional analog of the second derivative. It's the matrix of second partials. So we found that, and then we evaluate that at each critical value, and then take its determinant using this. Because we have a function of 2 variables, the Hessian is a 2 by 2, so you just multiply across this diagonal and subtract, and that's going to give you a number. If that number d is greater than 0, and the second partial with respect to x and the second partial with respect to y are both positive, it's concave up in the x direction, concave up in the y direction, and you're at a min. If d is positive and both of these second partials are negative, it's concave down in the x direction and concave down in the y direction, so you're at a max. Now if d happens to be negative, that means it's concave up in one direction, concave down in the other, or maybe in one of the directions the slope is 0. But in any case, we're going to have a saddle point there if d is negative. Now, if d happens to be 0, the test is inconclusive. Usually that means that you don't have an extreme value like this. You don't have this gradient equal to 0 at a point, at a moment, like at a particular location. You usually have a gradient equal to 0 along a curve when d is equal to 0 the whole time. So that's what we want to see. We want to know, with each of these critical points, what are we dealing with here? Now, in order to do that, the first thing we need is the Hessian matrix. So we need the matrix of second partials, which requires taking a lot of partial derivatives, which is why we needed another video. So keep this in mind. We're coming back to that. And let's write down our first partials. The first partial of f with respect to x was 2x times e to the negative x squared minus y squared times the quantity 1 minus x squared, I'll distribute the negative this time, minus 3y squared. Okay, now taking the derivative again with respect to x is going to require the product rule. If this is my first function and this is my second function, I'll get second partial with respect to x is derivative of the first, and I'm just going to write that down for right now, times the second plus the derivative of the second. Derivative of the second with respect to x is just, that's 0, negative 2x and 0, times the first, undifferentiated. So we're here now. Now the only thing left to do is to evaluate this derivative, but that requires a product rule as well. So that's our first function and our second function this time. So we'll have derivative of the first is 2 times the second, it's that exponential, plus the derivative of the exponential, derivative of e to some power is e to that power, times the derivative of the inside with respect to x, treating y as a constant. And derivative of this with respect to x, treating y as a constant, is just negative 2x. That's derivative of the second times the first. Remember, all of that is multiplying all of this. And this over here simplifies to negative 4x squared times the exponential. Now we could factor this further, and I think we have time. Let's factor it further. Inside these parentheses, I see these two factors have an exponential in common. They also have a 2 in common, so I'll factor out the 2e to the negative x squared minus y squared, and then I'm left with this times 1 gives me my first term, and this times what gives me my second. I got rid of one of the 2's. I'm still left with a negative 2x squared times e. No, I already got rid of the e, so that's gone. So I've got 2 times this times the quantity 1 minus x squared minus 3y squared minus 4x squared times the exponential. And I'm still hoping to be able to factor something out from everything. I think we can factor out the exponential from everything. If I think of this as a first term and this is my second term. So we have 2 times this times the exponential is our first. That times that gives us that. And then we're subtracting 4x squared. And I believe we could simplify that further if we wanted to. But we're going to plug in a bunch of points. You know what? We're going to evaluate this when x equals 0 or plus or minus 1, and when y equals 0 or plus or minus 1, so let's not worry too much more about the algebra. So that's the factored form of the second partial of f with respect to x. Now let's find the first mixed partial of f with respect to x, and then y. So I'm taking the derivative with respect to, it's still product rule again, that's a function of y, and that's a function of y. So I won't write this time. So the derivative of the first with respect to y, well, 2x is a constant with respect to y, so I can bring that down. The derivative of a constant times the function of y is the constant times the function of y. The derivative of e to this power is e to that power times the derivative of the inside with respect to y, treating x as a constant. well, if x is a constant, the derivative of that guy is 0, so we just get 0 minus 2y. So that's derivative of the first times the second. Plus derivative of the second with respect to y is negative 6y times the first. Okay, let's simplify this a little bit. I've got a negative 2x and a negative 2y, so that's negative 4xy times the exponential times this quantity. And over here I have a negative 12xy times the exponential. And if we want, we could factor further. I think I will factor just a little bit more. I'm looking at this is my first term and this is my second term. Well, they both have the negative 4xy in common, so I should factor that out. They also have exponentials, so I should factor that out as well. So this times that gives me my first term. And this times 3 gives me my second term. So we just end up with this. Now remember, we studied this fact earlier. If our functions are nice, and most of them are, the partial with respect to x and then y is the same as the partial with respect to y and then x. So we can just write that down. We don't have to do it again, which is nice. Now we need the second partial with respect to y. So we're taking the derivative of the partial with respect to y, and the partial with respect to y is on this other page. It's off the screen. I'm just going to read it off there and I'll write it here. Partial with respect to y was 2y times this exponential, and we'll distribute the negative. Okay, and now I'll call this my first function and this my second function. So we'll take the derivative using the product rule. We get derivative of the first times the second plus derivative of the second with respect to y. It's easy enough that I'm not going to write it out like this. I'll just compute it. There's derivative of this with respect to y is 0 because there's no y in it. Derivative of this with respect to y is 0 because there's no y in it. And derivative of that piece with respect to y is a negative 6y. So it's derivative of the second times the first. And this guy requires a product rule because I've got a function of y times a function of y. That's my first function and that's my second. So we'll have derivative of the first is 2 times the second plus the derivative of the second. Derivative of e to some power is e to that power times the derivative of the inside with respect to y. It's negative 2y. Times the first, it's a 2y. All of that is getting multiplied by 3 minus x squared minus 3y squared. And we will subtract 12y squared times the exponential over here. Okay. Woo! It's a lot. That's okay. We can handle it. I'd still like to factor a little bit further, make it a little bit simpler. We've got this in these brackets. I want to look at these guys separately. They've got a 2 and an exponential in common, so I'll factor out the exponential. Factor out the 2. 2 times exponential times 1 gives us our first term. And I've already factored out one of the 2's, so we'll have a negative 2y squared times the exponential is already out there. Negative 2y squared is all that's left. So it's that times that. That's the factored form of this expression in brackets, and I still need to bring that down. Okay. Now I look at these two guys, And I could factor out the exponential from both of them, but I really don't think it's going to save us that much time later when we evaluate these at our critical point. So I'm not going to. Yeah, these are our second partials. So let's calculate the Hessian at each critical point, and then look at the determinant, and then come to a conclusion for each point. So my first critical point, or here are my critical points, I'll just write them down. Our critical points were 0, 0, 0, 1, 0, negative 1, 1, 0, and negative 1, 0. And our original function was x squared plus 3y squared times e to the negative x squared minus y squared. Okay. Now we want to evaluate the Hessian at these points. And then we want the determinant of the Hessian, and then we'll do the second partials test for each point. So let's start with 0, 0. Find the Hessian at 0, 0. So we want the second partials with respect to x, second partial with respect to y, and then the mixed partials on the other diagonal. And we want all of these guys. Oops, first I want just the matrix, not the determinant of the matrix. I want the matrix evaluated at 0, 0. That's the Hessian. Okay, it's easy to plug in 0, 0. So let's go to our partials and plug in 0, 0 and see what we get. Second partial with respect to x, at x equals 0, y equals 0. And our second partial with respect to x is right here. Well, if x and y are both 0, that's e to the 0, which is 1. And if x and y are both 0, that's 0, and that's 0, and that's 0. So we get 1 times 2 minus 0, so we just get 2. Okay. Then let's evaluate this mixed partial at 0, 0. It's got an xy factor out here, so that's definitely 0. And the mixed partials are equal, so that one's 0. And now we just need the second partial with respect to y at 0, 0. So at xy equals 0, 0, this is e to the 0, that's 1. So we've got 2 times 1, so 2. 2 times 1 times 3. So 2 times 3 is 6. From over here, minus 0. So we just get 6. Okay, that's the Hessian at that point. Now the determinant of the Hessian at that point just comes from multiplying across this diagonal, so we get 12, and then multiplying across that diagonal, getting 0, and then subtracting. The determinant is positive, and the second partial with respect to x is 2, so that's positive. And second partial with respect to y is 6, also positive. That's not a coincidence. If d is positive, that means these both have the same sign. So that means our graph is concave up in the x direction, it's concave up in the y direction. And so f of 0, 0 represents a relative min. At 0, 0, our function is just 0 times e to the 0, so we get 0. Okay. Now let's evaluate this guy at x equals 0, y equals 1. Okay. Go back to all those second partials we calculated. We're substituting in 0 for x, 1 for y. So if x is 0 and y is 1, this is e to the negative 1. And then we've got 2 times 1. And we've got 1 minus 0 minus 3. So we've got, I'm just going to write it down over here. I know there's like a mess of writing. Just focus here. Second partial with respect to x at 0, 1 is e to the negative 1 times 2 times 1 times 1 minus 3, and x is 0. So that's minus 0. So we end up with negative 4, because that's negative 2 times 2 is negative 4, times e to the negative 1. So you have negative 4 over e. If x is 0 and y is 1, second partial with respect to x and then y, well, if one of those variables is 0, that's 0. So that means that's 0, and the mixed partials are equal to each other, so the other one's 0 as well. And then let's find the second partial with respect to y at 0, 1. So we're evaluating that at 0, 1 now. We have 2 e to the negative 1. I have 1 minus 2. If x is 0, that's 0, and then we've got 3 minus 3 times 1 squared. So this is 0, so that means this whole piece is 0. And then over here, we've got minus 12y squared, so that's minus 12 times 1 times e to the negative 1 again. So we get negative 12 e to the negative 1. All right. Or negative 12 over e. Okay, so this is our first critical point, and this is our second critical point. Now we are going to take the determinant of that. Negative times a negative is a positive. So the determinant's positive, so that means we have a min or a max. And the second partial with respect to x, and at that point is negative, so it's concave down in the x direction. And we're told that if this is positive, then they both should have the same sign, and they do. So this is negative, so it's concave down in the x direction and concave down in the y direction. So we've got a graph that looks kind of like this. So we're going to have a relative max at 0, 1. F of 0, 1 is, plug in 0, x equals 0, y equals 1. So we'll have 3 times e to the negative 1. That's a relative max. Okay, so we got a relative min at 0, 0, and a relative max at 0, 1. Okay, now we want to evaluate everything at 0, negative 1. Just going to put big dividing lines here just to keep us on track. Okay. X equals 0, y equals negative 1. Ooh, notice the symmetry. Every time I have a y in here, it's a y squared. So when I had a 1 before, well, it's not going to change the value if I change that 1 to a negative 1. So the second partial with respect to x at 0, 1 is the same as, or this at 0, negative 1 is the same as the second partial with respect to x at 0, 1. So this is actually the same as that. And at 0, negative 1, x is 0, so we get 0 here, and the mixed partials are equal, so we get 0 there. And then let's look down here. Are all the y's squared? Y squared, y squared, y squared, y squared. Yes. So that means that the second partial with respect to y at 0, negative 1 is the same as the second partial with respect to y at 0, 1. So we're going to get negative 12 over e here too. So the determinant is still 48 over e squared, which is still positive, and those are still negative, the second partials with respect to x and y. So we see a little symmetry here, don't we? Symmetry is nice. So it's concave down in the x direction, concave down in the y direction, and you have a relative max. F of 0, negative 1 is a relative max, and our function has a y squared and a y squared in it. So we're going to get the same value that we got last time as well. We'll get 3 times e to the negative 1 is a relative max. Okay. Ooh, 3 down, 2 to go. This is actually a really cool looking function. I've got a model of this that I show my students in class. If you go to Calc Plot 3D, search for this online. Calc Plot 3D. And then just plot this function. Graph it there. Just mess with the little app. I say little app. It's a big app. It's kind of a big deal. I think his name is Paul Seeberger. Got an NSF grant to create that app. It's wonderful. You should go there and graph this function and check out what it looks like. I think it's really impressive, and then you can actually see the mins and the maxes and the saddle points. You'll see all of this stuff. It'll make it a little bit more concrete for you. Okay, so that's an aside. Let's go back to classifying our critical points. And now we want y to be 0 and x and y, or the x values to be plus and minus 1. So y is 0 and x is 1. See what we get this time. And look for symmetry again. Are all the x's squared? Yeah. Are all the x's squared here? Well, these ones aren't squared, but we're about to plug in y equals 0, so it doesn't matter. Are all the x's squared down here? Yes. So I think we can evaluate this at plus and minus 1 at the same time. So x is plus and minus 1 and y is 0. Let's see what those partials are. So we'll have e to the negative 1. If x is 1, this is going to be 2 times the quantity 1 minus 2, so 2 times negative 1. And if x is 1, we get 1 minus 1 minus 0, so that's going to be 0. That whole factor is 0, so that's gone. And if x is 1, or negative 1, we'll have a negative 4 here. So we'll have negative 4 times e to the negative 1. Okay. And if x is plus or minus 1 and y is 0, this guy is 0 because of that factor there. The mixed partials are 0. And if x is plus or minus 1 and y is 0, we get 2 times e to the negative 1 times 1 times 3 minus 1, so that's 1 times 2. And y is 0, so that's gone. So let's write that out. Second partial with respect to y, writing it down here, at plus or minus 1 and 0 is 2 e to the negative 1 times 1 times 3 minus 1. So I end up with 4 e to the negative 1. Okay. Ooh, notice that. Concave down in the x direction and concave up in the y direction. So I think we're going to have saddle point, guys. The determinant at these points is negative 16 over e squared. That's negative. So each of those points is a saddle point. When x equals 1 and y equals 0, we get e to the negative 1. And when x equals negative 1 and y equals 0, we get e to the negative 1. These are both saddle points. I should say both are saddle points. Let's use complete sentences. Even though we're in math class, it's important. Even if we're not as good at English as those other guys, we should still try, because communication is important. It's not about just knowing the math, but being able to explain it to other people. Math is hard to explain. It really is, but we have to try our best to communicate what we know, so that all this knowledge that we have in our heads is worth something, so we can share it with the world, right? So it's not just for our own entertainment, but for everyone, and we can make the world a better place. So, yeah, that's my PSA for today. We've got 2 saddle points. We've got a relative max over here, and a relative max over here, and a relative min over here. Now, again, I just want to encourage you. That was the second partials test. If you want to check this out, if you really want to see it, search for CalcPlot 3D, just Google it, and graph this function. And then look for those mins and maxes. You have maxes when x is 0 and y is plus and minus 1. And you've got saddle points when y is 0 and x is plus and minus 1. And then you've got a min at 0, 0. So I encourage you to go to CalcPlot 3D or Wolfram Alpha and just graph this and see if you can see those 2 saddle points, those 2 maxes, and that min. So that's our example of finding relative extrema of a function of 2 variables.